Hi everybody, and welcome to Unit 5 Notes Part 2. Hopefully at this point you're getting really comfortable with writing out and balancing those chemical equations that represent chemical reactions. Today we're going to make things a little bit more interesting and talk about chemical reactions in real life. Just because we can write a chemical reaction does not mean that it will actually occur. Remember, for a chemical reaction to occur, a chemical change has to happen. All right. And just because, again, we can write them doesn't mean it's going to happen. This is especially true for single and double replacements. All right. So let me just take a second and tell you. If I give you a synthesis, a decomposition, or a combustion, you can just always assume that those reactions will take place. Okay, don't worry about that. They will take place. For single and double, you're going to have to do a little bit more work. So for a single replacement reaction, all right, to actually happen, the nonmetal in the compound has to be more attracted to the lone metal than to its partner. Well, again, because that lone metal needs to kick that partner out. So how are we going to tell which metal is more attractive? Well, what we do is we look at something that is called the activity series. And this is a list of metals in order of reactivity. A metal higher in the series will replace one lower. All right, on the back of your periodic tables, you have an activity series. And it tells you the top, all right, are your most reactive, and then going down to your least reactive. Okay, so, and you'll have this when you, do your practice sheets and when you are tested. All right, so on the list I've given you, which is just an abbreviated list of the metals, okay, but I'll only ask you ones involving these metals. Potassium is the most reactive, meaning it can replace any metal I would give you. Silver is the least reactive. All right, so let's see what this is going to look like. So, first off, let's take a look at the instructions. Look at the following reactions below. Based on the activity series, determine if the reaction will occur. If it does, write a balanced equation. If it does not occur, write no reaction. Feel free to pause the video now and give these three a try, or you can just hang on and I will go through them with you. Okay, so first up, let's go on ahead and write these compounds. It's really good practice. All right, so calcium chloride, calcium +2, chloride -1. So it's CaCl2, because I need 2 chlorides to go with that 1 calcium, plus copper. All right, and now before I do anything else, let's see if this reaction is going to happen. I'm going to check my activity series. All right, and when I do, all right, I'm going to find where calcium is. Oh, calcium's pretty high. All right, and I'm going to compare it to where copper is. Copper's down at the bottom. Copper is less reactive than calcium, so copper cannot replace calcium in this compound. So this reaction will not happen. The answer to this is actually no reaction. RXN is the abbreviation for reaction. Okay, let's go on to the next one. Aluminum nitrate, aluminum's +3, nitrate's -1. So that is AlNO3 plus magnesium. All right, now let's check the activity series. Let's find aluminum. All right, well, aluminum's right here. Let's find magnesium. Magnesium is above it. Magnesium is more reactive than aluminum. It is higher in the activity series. So magnesium can replace aluminum. So that means this reaction is going to happen. So I'm going to go on ahead and balance this. So the magnesium is going to kick the aluminum out, giving you magnesium nitrate. Magnesium stays +2. All right, so we're going to need 2 nitrates. And then that aluminum gets kicked out. I now need to balance. I see right away I have a 2 and 3 situation. So I'm going to put a 3 in front of magnesium nitrate to give me a total of 6 nitrates. I'm going to put a 2 in front of the aluminum nitrate. And now I need to balance my lone elements. And I am good to go. All right, so let's check our next one. Copper 2 iodate. Copper 2 means copper's +2. Iodate's always -1. All right, so that's CuIO3 2 plus zinc. Let's check to see if this is going to happen. All right, so I'm going to check copper. All right, well, copper's pretty low down on my activity series here. And then I'm looking to see where zinc is. Zinc is up here. Zinc is more reactive. it's going to kick that copper out. So this reaction is going to happen. All right, zinc in an ionic compound is +2, so that means I need 2 iodates. Copper is going to be kicked out. I check. I'm already balanced, so I'm good to go. All right, great. Just a final note about single replacement reactions. If you get a single replacement where the lone element is a non-metal, you can assume that reaction is going to happen because we're not giving you an activity series for non-metals. For the metals, you have to check your activity series just like we did here. All right, so let's move on to our double replacement reactions. All right. All double replacement reactions occur in solution, all right? Double replacement reactions occur between ionic compounds, and ionic compounds are things like table salt. They're solids. So in order to get them to react, we have to dissolve them. You saw an ionic reaction when you were watching the chemical reaction lab, when Maurice reacted the copper 2 sulfate with the sodium hydroxide. You saw those two solutions mixing, all right? Oftentimes you can have two solutions mix and they're not creating anything new, which means that there wouldn't be a reaction. In order for a double replacement reaction to occur, a precipitate, like that solid you saw in the lab, all right, a precipitate must be formed. Otherwise, all you have are just these ions floating around in solution and you're not creating something new. In chemical reactions, to be completely thorough, we need to use what are called state symbols. Okay? A state symbol is exactly that. It is a symbol that tells you what state the substance is during the reaction. The state symbols are as follows: S or Cr for a solid. S stands for solid, Cr is crystalline. It's just a different way of saying it. Both of those mean that your compound is solid. G is for gas, L is for liquid, and AQ stands for aqueous. Aqueous is when you have a solid compound dissolved in water. So aqueous means the substance is dissolved in water. It also means that it is soluble in water. To be soluble means you can dissolve, you can break into your parts. So how are you going to know whether something is soluble or not? Well, we're going to look at what is called the solubility rules. All right, and again, these are on the back of your periodic table. All right, these are your solubility rules. Okay, I'm just going to read through them, okay, kind of quickly. You certainly should read over them yourselves. Okay, and then I'm going to show you how to use them. Okay, group 1, which are your alkali metal elements, and ammonium compounds are always soluble. So if you see something that has a group 1 metal or ammonium, it is soluble. It will dissolve in water. Acetates, chlorates, and nitrate compounds are always soluble as well. Rules 1 and 2 will really help you because there's no exceptions to those. They're just nice, quick rules to constantly remember. The rest of our rules have some exceptions, so it takes a little bit longer. Any metal combined with group 17, your halogens. So this is a situation where we're talking about those halogens. If you see a halogen, they're soluble except silver, mercury, all right, and lead. Sulfates compounds are soluble except barium, strontium, your leads, calcium, silver, or mercury, okay? Finally, except for those in Rule 1, compounds with carbonates, hydroxides, oxides, sulfides, chromates, and phosphates are not soluble. Now, again, I know that this is a lot to take in. I'm going to show you how to use these as we look at some double replacement reactions. All right, so the first thing you're going to do, I want you just to pause the video, write the double replacement reactions for each of these. All right, and then we'll go through and use the solubility rules. So pause the video and go on ahead and do that. Okay, let's come back. I'm going to do these pretty quickly. All right, so magnesium chloride plus silver nitrate, okay, is going to give me magnesium nitrate plus silver chloride. Okay, I'm going to then balance this. All right, I know that I need 2 nitrates here and 2 silver chlorides. Great. Okay, so now let's check our solubility rules. All right, how you do this is you have to look at the compound and see what you're dealing with. I see magnesium. Magnesium's not group 1, it's not ammonium, all right? So I don't have a rule that always covers magnesium. So the rule for this compound must have to do with my other element, and that's chloride. Chloride is a halogen. It's group 17. So I'm going to look at my rule for halogens. Okay, any metal combined with group 17, so any of these compounds will be soluble except silver, mercury, and lead. Well, magnesium's not silver, mercury, or lead, so that means that magnesium chloride is soluble. So that gets a little AQ after it, meaning that it is soluble. It dissolves in water. All right, next compound, silver nitrate. Well, nitrates are part of your rule number 2. Okay, nitrate compounds are always soluble, so that is also aqueous. Okay, so now let's look at the products. All right, again, I'm at magnesium nitrate. Nitrates are always soluble, so that's AQ. Finally, my silver chloride. We already know from over here that chloride is a halogen and it has its own rule. So let's go back and look at rule 3. All right, so halogens are soluble unless they're with, silver. I'm with silver. So that means silver is insoluble. It will not dissolve in water. When this reaction occurs, silver chloride actually is a solid. It is your precipitate. All right, we also call this a precipitate, PPT for precipitate. Okay. I formed a precipitate, so this means that this double replacement reaction occurred. Okay. All right, let's look at number 2. Again, I'm going to go through the regular reaction very quickly. Sodium chloride, which is table salt, and ammonium phosphate. If they switch partners, it's going to be sodium phosphate plus ammonium chloride. All right, so again, let's go through. Sodium is part of group 1, so that's rule 1. Alkali metals and ammonium compounds are always soluble. Well, your sodium is an alkali metal, so you are always aqueous. Ammonium is always soluble, so you are aqueous. Let's look at our products. Again, sodium always, if sodium is part of your compound, if a group 1 element is part of your compound, you are soluble. Ammonium, same thing, soluble. So if you notice here, both of my products are aqueous. I actually didn't form a solid. I didn't form a new substance, because what's really going on is when these are aqueous, it means that they're floating around as their ions. I didn't create anything new. So this one actually doesn't happen. So I should cross this out and write no reaction. If you do not form a precipitate like we did up here, there is actually no reaction. So let's see if we get a reaction for number 3. Okay, so I have aluminum. Okay, I have, aluminum iodate plus lithium carbonate, and that's going to give me Al2CO3, aluminum carbonate plus lithium iodate. All right, so we're going to take a second. We're going to try and find our rules that go along with this. Okay, so acetates, chlorides, and nitrate compounds are soluble. I will tell you now, because I don't believe the rule is here. All right, aluminum iodate is soluble, so I'm just telling you that one. Sorry about that. I thought it was in the rules, but this one is soluble. Lithium is a group 1, so that is always soluble. Okay, let's look at our compounds. Aluminum carbonate. Is there a rule for carbonate? Let's take a look. Ooh, I forgot an I there. All right, let's take a look to see if I have a rule for carbonates, and I do. Rule 5, except for those in rule 1. So is carbonate with a group 1 or ammonium? No, it is not. So except for those in group 1, compounds with carbonates, hydroxides, oxides, sulfides, chromates, phosphates are not soluble. Okay, so this one is my precipitate, so it gets a solid. All right, lithium we've already established is always soluble, so there we go. Okay, so here we go. We formed a precipitate. This reaction happens. I don't forget, I need to balance this one. All right, so I need a 3 here, I need a 2 here, and I need a 6 here, and this would be my balanced equation. All right, so you're going to be using those solubility rules to help you figure out double replacement. So just to quickly review, activity series is for your single replacement, okay? Only single replacement. People tend to fall in love with activity series. Only for your single replacement. Solubility rules for your double replacement. Again, we're gonna have a lot of practice with this. Have a great day.